Hi! Welcome to another video lecture in college physics. We're in chapter 3, ready to start discussing projectile motion. Projectile motion is a case of kinematic motion, and our view of projectile motion is going to be 2D. That is going to be x and y direction of the motion, and importantly it's going to be a case of constant acceleration, kinematics for constant acceleration. That is, neglecting air resistance, the only acceleration in projectile motion is acceleration due to gravity. So now we're in chapter 3, and here, looking at this picture of a roller coaster, if we wanted to study the kinematics of the roller coaster, that is, the position versus time, velocity versus time, and the acceleration of a roller coaster, that would be an example of kinematics in 3D. And we have the tools actually right now to study a problem like this, roller coaster motion, kinematics in 3D, and that is because we've learned how to do kinematics in 1D for constant acceleration in particular. And if we understand how to do kinematics in 1D, we're really in the running to do kinematics in 3D, because as we're going to see, it's just a matter of repeating the same principles 3 times, one for each of the component directions. So we've already developed the tools that we're going to need to study kinematics in 3D if we wanted, and actually we're not going to spend much time with kinematics in 3D. We're going to go straight to kinematics in 2D, and in particular the case of projectile motion, which is what we're headed towards right now. But we've already developed the tools that we'll need to understand that. One of them is the idea of vectors. They're showing a displacement vector. Here's this helicopter, and we've learned how we can break vectors into their components. Here this path of the helicopter is being broken into its x and y components. So we're going to be employing the tools that we've already learned about. Okay, so here's what's coming up. Projectile motion. And here we can see an example of it. Soccer player kicks a ball. That ball now goes into projectile motion. He kicks it with some initial upward velocity going up into the red path. The red line is his curve through two-dimensional space. The vertical part, upward vertical, we're going to call the y direction, and horizontally to the right is going to be the x direction. And here, after some time, this vector s would be his displacement. Once he's right at the tip of this arrow here, this S arrow, that would be his displacement at that particular time. And here we're measuring his displacement from where he kicked it. We're going to arbitrarily call the location where the ball starts off from the origin. And so that S vector, as you can imagine, would be moving in time. It would just be following this ball along. And then when the ball got here to the tip of the arrow, that would be the displacement vector. And at that time, it would have this particular x and y components, but at any given time, the displacement vectors got x and y components. So that's what's coming next, our discussion of projectile motion. Before we start discussing projectile motion, which is kinematics in 2D, let's think for a second about how we're really in a position to study kinematics in 3D if we wanted. And we're not really going to do that, but we're in a position to start up on that if we wanted to. Now, to be honest, kinematics in 3D is harder than kinematics in 1D and harder than kinematics in 2D, but not that much. Conceptually, we do have the tools to study kinematics in 3D. That is for the case of constant acceleration. That's the case we're going to limit ourselves to. Okay, let's just think about what I'm talking about. So for an object moving around in 3D, say a bird, an airplane, Superman, whatever we want, there's an object could just move around in 3D, so the object makes this path in 3D. And so he's going that way. Now this path, as we know, is independent of any way we want to describe it, of any system that we want to use to describe it. Now this gentleman named Descartes, he's the gentleman credited with giving us the Cartesian coordinate system, and that's what we would going to quite naturally want to use to describe the motion of our object in 3D. So the Cartesian coordinate system, what would that be? So the Cartesian coordinate system would first be to get ourselves a set of three-dimensional axes. So here we could make that the y direction, say the up and down direction. Then now we'd be describing the motion in 1D, but here this curve is living in 3D, so we'll need also the x direction. And that would get us up to 2D. And if this object's motion was confined to 2D completely, we could describe the entire motion as being confined in a plane, the xy plane here, so it only would have an x and y component of its motion. Like projectile motion, that would be the case of projectile motion. Of course, this is not a projectile moving unless that projectile has a rocket pack attached to it. But if this object is living in 3D, then we also need some other axis. We'll call it the z-axis. That comes straight out us, this axis. So all these axes are orthogonal to each other, that is mutually perpendicular. X, y, and z, they're all mutually perpendicular. And we can use these to describe the position of our object. It's known as the Cartesian coordinate system. We can think about, okay, well, how will we do that? Well, here's how we could do it. So here's our object, say at this particular time. There's our object at some time t. He's right there. So that object now has something that we call a position vector. And that position vector would be its displacement, that is, it's a straight line arrow that goes from the origin of our coordinate system to right where that object is. Okay, so at any given time, you could draw an arrow from the origin to where the object is in its path, and that's the position vector of the object at that point on its path, point in time when it's at this point on its path. And now we can resolve the x and y components of this position vector. How do we do that? Well, we understand how to do vectors now. The way we would resolve the x and y components of our position vector, and the book calls it S, so I won't deviate from that. They're calling a position vector S. Let me call it also S. A position vector S. I could describe as its x, y, and z, actually since it's in 3D, x, y, and z coordinates. Well, how can we find the x, y, and z coordinate? All right, well, the way we do that is like this. So first we would drop a perpendicular down onto the xz plane. So just go to where the object is, take a plumb bob, drop that straight down on the xz plane. Then you go from the origin, draw a line from the origin to where that plumb bob of the position vector lands down on the xz plane. That's going to get you the x and z position. How's it going to do that? Well, what we got to do now is drop another perpendicular over to the x-axis. So you got to draw a line from this point in the xz plane, a line that goes perpendicular to the x-axis, a line perpendicular to the x-axis that meets this point right here. This will be perpendicular right here. Try to draw a little perpendicular on there. And same with the z. Go over to hit perpendicular onto the z. So that's also perpendicular. So we drop a perpendicular onto x, a perpendicular onto z. Well, now we can see what is the z component. What is the z component? Follow it out right here. You just go from here to there, and that's the z component right there. What's the x component? Okay, the x component, you go from the origin right over here to where that perpendicular hit on the x-axis. That's the x component. What about the y component? We just do the same thing. That one, we just hit a perpendicular right over from where he is, right onto the y-axis. So that's perpendicular, and it goes right over to there. And up to that point, that's the y coordinate of the object. So now we can completely track the object's x, y, and z coordinates. Now if we can track the object's x, y, and z coordinates, then we have a complete description of the object's motion along its 3D trajectory curve. That is, all the equations we developed for 1D will work. We just need 3 of them now. And here we're going to assume constant acceleration. And the acceleration is a vector, by the way, and it's constant. So that acceleration is a vector, and since it's a vector and it's constant, in this case it would have 3 components. Since there's an x and a y and a z direction, the acceleration vector will actually have 3 components. And each of those components will be constant. Since the acceleration vector is constant, each of its components have to be constant. So then what will we get? Just considering that, so the x part of the motion, we would have, as we had before, we would have x is equal to x0 wherever it starts, plus average velocity in the x direction, though, the average x velocity times t. And the average x velocity we would get just as we had before, and we would have an equation for it actually, the average x velocity. The average x velocity is going to be given by the equation we had before. Be the final x velocity plus the initial x velocity over 2. Okay, because we have constant acceleration. This applies for the case of constant acceleration, this equation that I just wrote. And that indeed is the case. So we'll have this equation, and we'll have all the other equations that also came along from 1D kinematics. So we'll have that the final x velocity will be equal to the initial x velocity plus the acceleration times time. In this case, it'd be the x acceleration times time. Then, as before, using these three equations and eliminating for the average velocity and for the final x velocity, we would have equations like we had before, x equals x0 plus the initial x velocity plus 1/2 t squared, and so on. So we would have all these equations, and in particular these two equations, and I would have equations like that, the same kind of sets of equations for each of the component directions. So say for the y direction, for example, we would have a similar set of equations. Vy is equal to vy0, whatever it starts off at, plus how it's accelerating in the y direction. It's y component of the acceleration. And similarly, y will be equal to wherever it starts off at. I'm just replacing x's and y's here and just reusing this equation. I'll get us another same equation, except instead of x's, I have y's. Same kind of kinematic equation, ayt squared. And I could write an identical set of equations for the z kinematics that would give me the z component of velocity and the z position. Just replace x's with z's and write another set of equations. You can see just how to do it. I'm running out of space here, so I'm not going to bother. Especially too, since we're about to go to projectile motion, where we're only going to be considering motion in 2D. That is, you could think if this is a projectile, once I shoot that projectile, if there's no air resistance or rocket packs or anything like that to make it curve out of its path, then that motion would lie all along 2D. If this motion is projectile motion, it would remain in a plane. And if that motion remains in a plane, that's two-dimensional motion. And then if I like, if this was the motion and it stayed in a plane, I could just rotate the x-axis, could rotate the x-axis to be right along this red line right there, just rotate that over, and then now the z position would constantly be 0, so we could just throw it away, and all the motion could be completely described just by the x and y coordinates. That's what I'm saying, and that is the case for projectile motion, which we're about to get into that. So to summarize what we learned about kinematics in 3D, for the case of constant acceleration, what we're going to have is a set of equations. They're formally the same. I want to say identical. They're not quite identical because they give you the motion corresponding to each coordinate direction, that is the x, y, and z directions, mutually perpendicular directions, coordinate directions in the Cartesian 3D coordinate system. And by using each of these equations to independently track the velocity and position of each of the three coordinate directions, then you can reproduce the motion. So at any given time, if you know the x, y, and z position of the object, and you know how fast it's going in the x direction, how fast it's going in the y and z direction, then you can completely reproduce the motion. In fact, just with the position equations alone, just go to a particular time. If you know the initial position, you know the initial velocity, you know the acceleration, then just put in any value of time you want, and then you'll get the position, x, y, and z position at that time, and then just go out, say it's sometime over here, for example, just plot the position there, and then you can even draw a new position vector going out to there. That will be your new x, y, z position at some later time, and so on. So the equations we develop for kinematics in 1D, now we can see for the case of constant acceleration, give us a complete description of kinematics in 3D. Alright, but now we're going to go to kinematics in 2D because that's sufficient for projectile motion. And that's the case that we're going to be studying in particular. So to study kinematics in 2D, let's redraw our coordinate system with just x and y components. And let's get rid of the z component of acceleration because there is no z component. We're confining motion to 2 dimensions. Projectile motion all takes place in 2 dimensions. So now for projectile motion, all our motion is going to take place in 2 dimensions. That is in x and y coordinate directions. So I'll have a y coordinate and an x coordinate. So let's take a minute to look at what our projectile motion is going to look like. We'll go ahead and use PhET labs and get an idea of what some of our variables might be. In particular, we're going to want to figure out what our acceleration vector is going to be, our constant acceleration vector. So here's our PhET labs projectile motion sim, and we're going to go ahead and start taking a look at what our projectile motion is going to look like. First off, we'll just shoot it. See, okay, so there's projectile motion. And we can move this cannon around, do different shots of projectile motion. And for our projectile motion work, we're going to be ignoring air resistance. For one thing, since I'm going to be ignoring air resistance, I might want to see how big of an impact that's going to have on the projectile motion that we're going to be considering. So here, let's just turn the air resistance on for the pumpkin and shoot him. Okay, so there's the pumpkin shot with air resistance on. And let's turn the air resistance off and shoot him again and see how much of a difference it made to the motion. Okay, it made a little bit of a difference. Let's see, so before here he went 22 and over here he's going like 25 meters. So in that case it makes some difference. So sometimes you can't ignore air resistance. However, in many cases you can ignore air resistance in projectile motion. So if the speeds are low, you can ignore air resistance and projectile motion. That's one thing. Turn the speed down, say go to 5 meters per second, and then look at projectile motion in that case, and then now add air resistance and see what the difference is. So when the speeds are low, there's really not that much difference. Now that was the same pumpkin that we just shot before, where they're for a fast initial speed, 15 meters per second, going back to the default. There was a little bit of difference in the projectile motion for that pumpkin. But if we use another kind of object that are more air resistant, like say a tank shell, now that's going to go ahead and ignore air resistance to quite a good degree. So there's without air resistance, and I'll turn the air resistance on for the tank shell and reshoot, and we can see really no difference. Air resistance, we'll turn off the air resistance, reshoot, and it just replaces the trajectory curve with a new trajectory curve that you can see is completely the same. So this tank shell, for all practical purposes, ignoring air resistance, and that's what we're going to do, because when we ignore air resistance, what we get is kinematics in 2D for constant acceleration, and that's a straightforward example of 2D kinematics that we can handle with our current set of kinematics equations, our current understanding, our current model of kinematics. Honestly to say, if you introduced air resistance, then things do get quite a bit more complicated. And certainly when you first go ahead and learn a subject, when you first go ahead and learn something like how to use kinetic equations to calculate projectile motion in 2D for the first time, you're going to want to ignore air resistance. You're going to want to look at the simplest case possible. And as you can see, it's certainly not a bad idea to go ahead and ignore air resistance. So for this case, for this tank shell, we can see that's ignoring air resistance for all practical purposes. So not only does it simplify the equations, it just makes good sense to ignore air resistance, especially for an aerodynamic object like a tank shell, or even for not so aerodynamic objects at low velocities. So let's go ahead and look at what our acceleration vector is going to look like. Look at acceleration vector here, total and components. So let's go to slow-mo and shoot our projectile. Here we're shooting a pumpkin, and there we saw the acceleration vector. Maybe I'll just go to components and see what that turns out to be. Well, okay, so components is one component pointing straight down. Try total, shoot. So there's our acceleration vector. Here's two different pumpkins being shot. Here, I'll shoot another one. Go for a second. So it's three of them. So what are we seeing about this acceleration vector? Well, what we're seeing is this acceleration vector is acceleration due to gravity, and it's constant, and it's pointing straight down. I can see the value of the acceleration vector is 9.81 meters per second squared. Generally, we'll just use 9.8, go to 2 sig figs. We can also look at the velocity vectors. Go to slow, shoot them here. So that's the velocity vector. We can see the velocity vector is not constant in time as we shoot him. Let me put it on pause, shoot him again. Okay, so he's being shot. It's on pause. I click shoot. So the projectile is being shot. Here it's a cannonball. And what you're seeing here, this green arrow, is the initial velocity vector of the cannon. That's the velocity at time 0 that he's going to shoot out of the cannon with. It's his initial velocity. We can look at the components of that velocity and the total with components. I can either look at total or components. So that's the total velocity vector. Those are its components. It's not letting me show both at the same time. I go to intro if it will. Okay, so it looks like an intro. I can see the total velocity and its components. So the thick green arrow is the initial velocity that we're going to be shooting the projectile, and its components are drawn on here for us. We can see that this horizontal component, that's the x component of the velocity. And here it's the initial x component of the velocity. The vertical component is the initial y component of the velocity. And you can see that the total velocity is the sum of the x and y parts of the velocity, because here's how I could get the total. First I go up in the y direction, and then just follow over horizontally the x component of the velocity. So if I just took the x component of the velocity, if I could take this arrow, it won't let me do it, but if I could drag it up and put the tail of the x component of the velocity at the tip of the y component of velocity, then by doing tip to tail addition of the components, the x and y component, I would get the total velocity vector. So that's how components work. If you add the components using tip to tail addition, summing the components gives the total vector. Summing components for any vector will give the total vector. Now let's look at how the components of the velocity change with time along the trajectory path of the projectile. We'll go to slow motion and look at it. So can you see what's happening? The x component of velocity is not changing, and the y component is changing. Shoot him again. Watch that. The x component of velocity remains constant, while the y component of velocity changes. And that is, of course, because of the acceleration vector. Remember, the acceleration, and I've added it now, just points straight down. So there is no acceleration in the horizontal, because there is no horizontal component of acceleration. And since we're calling the horizontal direction the x direction, that means there is no x component of acceleration, and thus there is no change in the x component of velocity. And you're seeing that play out right there. The only component of velocity that changes during projectile motion is the y component of the velocity. So now, armed with this knowledge, we can go ahead and reduce our 2D kinematic equations for the special case of projectile motion ignoring air resistance. So now we understand what our acceleration should be for projectile motion. So here's our acceleration vector. It's got two components, x and y component, and we can see that the x component of acceleration needs to be 0 because the velocity stays constant in the x direction. The horizontal component of velocity stays constant for projectile motion ignoring air resistance, like we saw. And then the y component is straight down. It's minus g, acceleration due to gravity, straight down. Well, here g is 9.8 meters per second squared. Acceleration due to gravity, straight down. So here's our acceleration for projectile motion. It's just got one component that's not 0. That's the y component. So now we can go ahead and put that in to our projectile motion equations over here. So the y velocity equation then is vy0, whatever the y velocity starts off at, the y component of velocity starts off at, minus gt, because the acceleration in the y direction is minus g. In the y position equation, similarly, we just replace the y acceleration with minus g. So this becomes minus 1/2 gt squared. Now for the horizontal components of our kinematic equations for projectile motion, the x components, we just replace ax with 0. So replacing ax with 0, the second term in the velocity in the x direction, or x component of velocity, disappears. Similarly, so now we have our kinetic equations, 2D kinetic equations for projectile motion. Here are the equations that give us the x components. And we see that the velocity in the x direction is just whatever it starts off at, vx0. And the x position is, whatever it starts off at, x0, plus the x component of velocity times time. And typically, usually, unless there's a good reason not to, we'll just go ahead and put x0 equal to 0. So let's say I shoot the projectile from here, like you remember the FET cannon. We could say this is how we shoot the FET cannon. This is our initial velocity that we shoot the FET cannon. Then this would be the initial height. Put that y0. That's how I like to do it. Make y0 be the initial height. We could adjust it, the coordinate system, so that the cannon's always fired from an initial height, y0 equal to 0. That's something else you could do, but this is how I typically do it. As long as you're consistent, you figure out what you're doing and stick with it, you'll get the right answer. And here, then I'm just going to be making x0 equal to 0 down here, so I'm going to be shooting, so where I'm shooting it from, the starting position, is x0 equal to 0. And then in that case, I will just have x vx0 is t. So these will be our x component equations. This one here is pretty darn simple. This top one, usually you take this to be understood. Once you do a few example problems with this, it become pretty clear to you that vx equals vx0 is understood. Whereas the y velocity, that's not constant like we saw. The y velocity is whatever it starts off at, the y component of velocity, minus acceleration due to gravity times time. So here, how are we going to break our initial velocity into components? Okay, so we see we have an initial y and x component of velocity. Let's look at breaking those up into their components. To break the initial velocity into x and y components, we draw on the x and y component of velocity so that v0, that is the magnitude of the initial velocity, forms the hypotenuse of a right triangle where its x and y components are the side adjacent and side opposite. So the side adjacent is going to be the initial x velocity, side opposite is the initial y velocity, and here's if theta right here is the initial angle above the horizontal that we shoot the projectile at, so theta is the angle of attack of the projectile, then we can use our trig to resolve the x and y component as follows in terms of the magnitude of the initial velocity, that is the speed of the FET cannon in this case, the initial speed of the projectile, v0, and this will be cosine, picks out the side adjacent, the cosine of the angle. And this one will be given by, again, the initial speed times the sine of the angle. So now if we're given the initial speed and the angle, we can use our little bit of trig here to resolve the x and y component of the initial velocity vector, this initial velocity vector. And then with that, we can just go ahead and plug those values into our 2D kinematic equations. Here are equations for the vertical component, the y component of the velocity and position, and similarly the horizontal component of velocity and position, that is the x equations. So that wraps up our derivation of the 2D kinematic equations for projectile motion. Next we're going to want to do some examples of solving projectile motion problems using these equations.